work on circuit private multi-key threshold approximate homomorphic encryption by Kamil, Kluczniak and Giacomo Santato, and Giacomo will give the talk. So are we ready, Giacomo?
Giacomo Santato, a PhD student at CISPA. Unfortunately, I was not able to join you in person in Toronto because of health issues. But I wish you all an amazing and productive FHE.org conference, as it was in the past editions. I hope to be able to meet all of you in other future events. Today, I'm going to talk about secret private, multi-key, and threshold approximate homomorphic encryption. This is a joint work with Dr. Kamil Kluczniak. As you can see, the title is very long, so we are going to split it and the conference in 3 different parts. In the first part, we are going to introduce some basic concepts about approximate HE, and in particular about the CKKS scheme. And after that, we are going to deal with the 2 main topics of the talk. Secret privacy, what it is, how it works, and what are the problems of dealing with it in the approximate setting. And after that, we are going to talk about multi-party HE. This is both multi-key and threshold HE. We are not going to separate them much because of time constraints, but we are going to analyze it in a approximate setting, and we are going to talk in detail about the connection between multi-party HE and secret privacy. Let's start with the introduction on approximate HE. We all know what HE is by now, and that in particular it allows to operate on encrypted data. To be more specific, you can encrypt a message, homomorphically evaluate a function on the ciphertext, and then when you decrypt the result ciphertext, you obtain f of m, so the function evaluated on the message. This is true for the main HE schemes, BGV, BFV, TFHE, FHEW, and many others that we are going to refer to as exact HE schemes. But there is a class of HE schemes that does not satisfy this condition. In particular, the approximate HE schemes, the most famous is CKKS. When you do all this construction, only returns an approximation of the result f of m, and not the exact f of m. As we can see in the slide, the result of the output here is f of m plus an approximation error e. Immediate question is, why use approximate HE then if is less precise than exact HE? Well, it is suitable for many applications that already works with tolerating approximation. Therefore, all the applications that work with floating point numbers like data analysis, inference to machine learning model, machine learning training of models, and also because most of the approximate HE schemes, they operate on real and complex number, something that is not true for most HE schemes. So they are good for different kind of applications, and they allow you to homomorphically evaluate also difficult functions by considering some polynomial approximation of these functions. For example, let's just think about Taylor approximation. Let's now talk about the main approximate HE scheme, CKKS. CKKS allows to work with real and complex number thanks to its encoding and decoding operations that allow to operate on these numbers by mapping them on and from Gaussian integers. When we are dealing with Gaussian integers, we can just consider them as polynomial, in a cyclotomic ring, and after this we can just use the ring LWE assumption to encrypt them. In fact, fresh encryptions of CKKS of a message is a pair B and A of polynomials, where B is the secret key times A plus the message M plus a Gaussian error E. The decryption instead, it's simply B minus secret key times A that outputs M plus E, where E is the same ring LWE error. This is clearly an approximation of M. The rising usage of CKKS in recent years brought to improvements in reducing the approximation error and also to optimizations in the bootstrapping techniques. During the last years, though, the cryptographic community noticed that properly analyzing the security of CKKS was more difficult than expected. Even if the original CKKS scheme in 2016-2017 proved the scheme to be indCPA secure under the ring LWE assumption, some years later, Lee and Micciancio showed a full key recovery attack that was possible when obtaining the error of enough decryption. In fact, knowing f of m allows to retrieve exactly the approximation error after decryption. This is easy. After decryption, we just obtain f of m plus e. Subtracting f of m allows us to retrieve the approximation error. This approximation error, as we have seen in the last slide, it's exactly the ring LWE error. And revealing the error of the ring LWE assumption is a problem for security. A year later, a team led by the same authors suggested a fix to the CKKS scheme by adding a post-processing phase with the addition of extra Gaussian noise during decryption. To properly address these attacks in the security analysis, they also introduced an extension of the indCPA security called the indCPA D security definition, where the D is linked to the decryption oracle that the adversary is given. Having seen that studying CKKS analysis sometimes might carry additional challenges, we decided to analyze more in detail secret privacy in the Approximate setting. This is the first main topic of the talk. Keeping the function secret. In many applications, it is important to keep the function that we are homomorphically evaluating a secret. Some examples of these applications might be private set intersection, inference to machine learning models, or analysis of genomic data. Let's make a practical example of this. If we are performing a privacy-preserving machine learning inference by using some homomorphic encryption scheme without any additional property, then we risk to reveal some information on the model that in this case represent the function that we are homomorphically evaluating, f, to an adversary. Secret privacy is exactly a way to characterize this security risk. Secret privacy is a security definition for HE schemes. And while in general the main focus in security definitions is on the message that the user is encrypting, secret privacy studies the secrecy of the function that we are homomorphically evaluating. The objective of this definition is to not reveal any meaningful information to the user except for the final result of the computation f of m. This, we repeat it, is not automatically guaranteed by the homomorphic encryption definition, and we need some additional requirements. Here is a high-level comparison between two security definitions. In the CPA, maybe the most famous cryptography security definition for when encrypting messages, and secret privacy. As an example, we are considering this protocol between a client and a server, where the client, who owns the private key, the public key and the secret key, encrypts a message M, sends the ciphertext to the server, and the server, who owns the public key and the function F, homomorphically evaluate this function on the ciphertext, and then sends back the resulting ciphertext to the client. The client concludes the algorithm by decrypting this ciphertext and obtaining F of M. In the first case, in the CPA security, we see that the adversary, in red, is the server. And the server, after the execution of the algorithm, tries to understand more about the message encrypted by the user. In the second case, instead, the adversary is the user who knows the secret key, we recall it, and it tries to get more information about F, even if he already knows F of M from the algorithm itself. Let's now talk about secret privacy in the exact HE setting. This is a well-studied topic that was introduced directly in Gentry's PhD thesis. And the most used definition takes the ciphertext after the homomorphic evaluation of the function F and requires to statistically simulate it by knowing only the public key and F of M. There are many known techniques for ciphertext sanitization that allow to achieve this secret privacy definition in the exact setting. But unfortunately, when trying to adapt this definition to the approximate setting, there are some problems that arise. In particular, this definition implicitly requires the correctness of the scheme. In fact, the ciphertext on the right is not an encryption of F of M, but it's rather encrypting F of M plus E. Also, the error obtained by the adversary is tightly associated to the ciphertext, and the magnitude of this error already reveals information about the function, like the size of the circuit, its topology, or even its multiplicative depth. In particular, we briefly recall the noise growth rules for CKKS evaluation to see the reason of this close relation. With addition, the error in the resulting ciphertext is just the sum of the original errors. With multiplication instead, the error growth tends to be much bigger, and it is also directly influenced by the encrypted messages. Since we express every function that we want to evaluate as a composition of addition and multiplication gates, it is easy to see why the noise growth is so closely related with the multiplicative depth, for example, and the topology of the function as a circuit. In our paper, we decided to introduce a new relaxed secret privacy definition that works also in the approximate setting. We decided to call it INDCP, Indistinguishability Secret Privacy. In this definition, the adversary, in red, chooses a message M and two functions F0 and F1, such that F0 of M is equal to F1 of M. After that, he gives to the server a non-history generated encryption of M. The server, as always, homomorphically evaluates one of the two functions on the ciphertext and returns the resulting ciphertext to the adversary. The adversary, knowing only F of M that is equal for F0 and F1, needs to guess which of the two functions was chosen by the server. Here are some of the results we have obtained. We modified the CKKS scheme and made it secret private under our new INDCP definition. We did it by adding a post-processing phase to the CKKS evaluation. This post-processing consists of adding a fresh encryption of 0 to the ciphertext and then adding a Gaussian noise to the B term of the ciphertext. We performed an extensive analysis of the optimal amount of Gaussian noise to add by using KL divergence. We obtained tight parameters showing that an attack with non-negligible advantage exists for smaller amount of noise. After that, we generalized our results for different function spaces, and we also wrote explicit parameters for application to privacy-preserving machine learning inference. In this last section, we talk about the second main topic of our presentation, multi-party HE in the approximate setting. Let's start by recalling what multi-party computation is. MPC is a well-known cryptographic primitive that allows multiple parties to cooperate together in order to evaluate a function. At the end of the execution, each party learns the final result, f of M1, M2, M3, M4, without learning anything else about the input of the others. One of the many ways to construct MPC protocols is by using HE. And in particular, MPC protocols constructed in this way guarantees low communication costs and low computation client side. We give now a high-level view on how to construct MPC by using HE schemes. We consider a fixed set of two parties in the approximate setting. The setup and keychain phases are different between the multi-key and threshold case, so we are not going to focus much on them. After obtaining the key pairs, the parties encrypt their messages and then homomorphically evaluate a chosen function of them. In this way, they are able to obtain a common ciphertext containing the final result. After this evaluation phase, we consider the decryption phase. This phase exploits that the decryption of the single-party HE scheme is linear with regard to the secret key, as we can see from the first formula. So each party can compute its own partial decryption, and then we can combine them together to obtain the final result. Additional noise must be added to each decryption share. Otherwise, as we can see from the second formula, the one of partial decryption, an attacker could just retrieve the secret key by solving a linear system. Finally, as we can see in the image, we obtain the final result of the evaluation, that is the evaluated function f of M1 and 2 plus the approximation error plus the additional noises that we added to secure the partial decryption phases. The relation between multi-party HE and circuit privacy. As shown in the picture, it is possible to achieve circuit privacy using two-party HE by homomorphically evaluating a universal circuit. A universal circuit is a function that takes as input another function f from the function space and a message m from the message space, and that outputs f of m, so the function evaluated on the message. It is folklore belief that this construction reduces the amount of additional noise required. Here are the results we have obtained for this section. We conducted a security analysis on the multi-key CKKS scheme. We modified it by adding a post-processing in the evaluation phase, and we quantified the noise flooding in the partial decryption phase. We introduced a new security definition that allows to achieve secret privacy that considers the impact of partial decryption and of the NDCPAD related attacks. After that, we did an extensive analysis of the optimal Gaussian noise using, again, KL divergence-driven analysis. We obtained tight parameters showing that an attack exists for a smaller amount of noise, and we also focused on applications by providing tools for security efficiency trade-offs. We conclude by talking about some work in progress. Many recent schemes are using Renyi divergence to achieve exact threshold FHE. Using divergences prevents from achieving security definitions that involve statistical simulation, as the ones that were commonly used for this primitive. So each one of these papers introduces at least one new game-based security definition. That is why in our paper we conducted an analysis of the new security definitions. We did a survey with comparison among them, and we provided attacks against the two definitions that were unsuitable for use. We also obtained an uninstantiability result of a random oracle transform from one-way CPA security to indie-CPA security. So we showed that every time we substitute the random oracle with an hash function in this transform, the transform does not work anymore. Thank you for listening to my talk. You can find the full paper available on the zip link. And now I will reply to any question via Zoom.
Any questions?
Hi, thanks for the presentation. In the game in which the user try to guess the function f0 of f1, do you have some restriction of the function like in the CPA game in which m0 must be of the same size as m1?
We give different versions of the game where the function space is chosen at the beginning, and depending on the function case, we obtain different parameters. So, for example, a restriction could be having a fixed maximum multiplicative depth. So, we studied in particular cases of polynomials of a maximum degree or with a maximum number of variables.
Thank you.
Yeah, to my understanding, the main uses of CKKS and Approximate AG is actually when you modify it to get exact AG. So, I mean, correct me if I'm wrong. Couldn't you just redefine the plain text space so that you get and do a compose with some rounding and so on to get an age, like exact HE, and then the whole analysis is just the same?
In some use cases, yes, you can just restrict in an artificial way the parameter space and try to contain the error to not influence the part of the plain text you want to save. But this is not the only use case of CKKS, and as I mentioned in the slide, you can embrace this approximation and start approximating also the functions. So if you want to evaluate sinus, cosinus, you can just evaluate the polynomial approximation on them, and you know that the error will be inside the plain text. You are not removing it anymore. So in some cases, yes, you can just reduce this again to the BGV, BFV analysis, but for the full use cases, no. There are some times where you just use CKKS, leaving the approximation inside.
Thank you for the presentation. In the example you've given of threshold or multi-key FHE, does it matter significantly whether you are in the public key setting or symmetric key setting?
In our analysis, no. In fact, the multi-key and threshold analysis are quite similar because we were mainly focusing on adding to the security definition the study of partial decryption and of indie-CPA-D-like attacks. So we didn't focus much on that part of multi-party HE. We focused mainly on decryptions.
Thank you.
Okay, let's thank the speaker again for answering the questions.